Yes.
Good afternoon, everyone. I'm Michael Butcher, President of the Franco-British Data Society, and I'm the chair of this event. Dassault Systèmes and the Franco-British Data Society, with the support of the French Embassy, Owen Mitchell and Data Learning, are delighted to welcome you to this webinar on new energy, the digitalization of nuclear. The Franco-British Data Society has as its principal aims the bringing together of the data and AI communities on both sides of the channel, the advancement of public education, and the development of human resources for the digital economies of our countries. I dare to say that this event takes full account of all these aims. Speakers will reflect on how digitalization and virtual twins can support the transition to sustainable energy and the cross-fertilizations of ideas and knowledge from other industries. I will introduce each speaker immediately before they speak for no longer than 12 minutes. This should leave us about 10 minutes for questions. Our first speaker is Mel Temple, 3DS Strategic Delivery Director at Infrastructure, Energy and Materials Industries, Dassault Systèmes. Mel, good morning, or rather good afternoon.
Good morning, thanks Michael. Yeah, so as an introduction, I've been working in the PLM industry for several decades. Where I'm going to start is to reflect on some of the industry digitization journeys that have been happening outside of the nuclear industry, predominantly in aerospace and defense and automotive sectors. For several decades, companies within these sectors have been heavily investing in digitization capabilities. In many cases, it was first of a kind attempts to move to a digital footprint, and obviously they faced a lot of challenges for the first time going through that process. The key driver within them industry areas was about the increase in product complexity that they had. So at a product level, the electromechanical aspects, and then coupled with software as well within their product sets, it became very, very complex and needed more digital capability to manage the evolution of the designs. They also needed to collaborate much more. No longer did you have a single company taking a product to market. It was always a collaboration through risk-sharing partnerships. And in a number of cases in the defense sector, you had multinations working together to bring a program through and take a product to its final production level. So the key aims were really around gaining competitive advantage through increased innovation. It wasn't just about the digital aspects of it. There was a large move to reduce the amount of physical prototypes that were produced, much more advanced simulation being applied. And again, collaboration and productivity were key drivers, and to bring the product to market a lot quicker than what had been experienced before. One key theme around quality was achieving right first time and on the design. So it was about trying to bring these products to maturity points. Again, reducing the dependency on physical prototypes, basically producing a design and qualifying a design in a digital sense before you even commit to tooling and the manufacturing process. So it was about becoming more predictable, not only on schedule, but in terms of cost and quality. So, but obviously, as you produce more digital data, you need to exercise a level of control over that data throughout the life cycle. So getting it correct in terms of the appropriate level of control and change management of the configuration of the product over that period of time was key as well. And there was a lot of learning in that area. So overall, they were applying product lifecycle management through various generations of enablement, moving to a virtual design and simulation, moving away from physical prototypes, and then trying to get to a point where they had more seamless delivery of data to the downstream processes such as manufacturing, and that's where a lot of the attention was put. Right, I don't want to be overly negative about the complications that were experienced within these industries. Fair to say that a lot of their investment was built around quite ambitious business cases with a high return on investment over a short period. And at the time, I don't think there was a full appreciation of some of the technical challenges and certainly some of the cultural change challenges that they faced. Many of these large-scale programs went over multi-years as transformation programs, and they didn't always achieve the objectives that were set out within those business cases. The kind of challenges they faced were predominantly the technology constraints that they had to live with were very real. As they increased the complexity of their data sets, they found that actually the limitations of the technology that they were applying meant that they had to make some appropriate decisions around the complexity of the data sets in order to achieve an acceptable performance of the systems. There was also a lot of complexity built into the architecture. They tended to be a best of breed approach in terms of capabilities selection, so very engineering focused in terms of capability selection. But within that, you also had different engineering disciplines making their own selection of what tools they wanted. And obviously it was very much based on their functional capability, without much focus around how the data that was being produced could flow across the life cycle and down into the downstream processes. To counter that, there was a lot of investment on bespoke interfaces. There was a lot of to drive more functionality. There was a lot of customization of some of the capabilities and the enablement that had been produced, to the point where it became very, very difficult to take the standard softwares that had been applied and take them through upgrade paths. And they became increasingly more difficult to upgrade because of the level of customization and complexity that had been built in, even to the point where the data sets themselves became unique formats that were bespoke to that company. And in general, there was a lack of industry standards around data. Over time, there was a progressive recognition that this was very important for the exchange of data across the different partnerships. And to avoid problems, we found companies being much more prescriptive over what systems were being used and the standards of data that had to be applied. Now, they weren't being done at industry level, they were being done as part of a consortium or program of work. So examples would be Lockheed Martin on Joint Strike Fighter basically prescribed that the software packages that had to be used, not only those software packages, but also the release levels and versions of them software packages. And everyone had to upgrade at the same time across their collaboration partners. So eventually there was a recognition that value could only really be realized through as part of a transformation program of work, with the objective of balancing the people factors, the process optimization, and the enabling technology across the whole ecosystem. So you had to look beyond the boundaries of your own company. And if you were participating in a collaboration, you basically had to have everyone moving together at the same time across that ecosystem. So that was a historical view. Things have progressed significantly. So I just want to run down some of the latest methods and approaches to dealing with some of these challenges. So there is a move away from these large-scale multi-programs of work in bringing PLM capability into use. It's within our own company in Dassault Systèmes, we apply what we call a value engagement method. And what we do is we look at the capabilities and how quickly we can release value to the customer. That goes through a cycle of analysis, an evaluation, and we're looking at making sure that from a roadmap point of view, the things that matter most are being delivered first. And part of that is an agile delivery framework that sits behind that, which is constantly looking at what the need and value is, and making sure that appropriate prioritization is being made to a backlog, and those things are delivered incrementally. So we're not waiting multiple years before the business users get to see something. We're continuously delivering incremental drops in capability to the business users. When we talked about scalability, the technology stack has completely changed since the previous decades, where there was a real challenge. We now have scalable solutions on the technology side of it, whether they be scalable data center capacity, or whether they be cloud services. Those options are now there to alleviate some of them scalability and agile scaling up of technology. There is a general view now across a lot of the industry areas that customization is not a good thing. It's not a good place to be in. You really need to be taking out the box capability from software vendors, applying zero customization, which now enables you to be quickly upgrade through the upgrade paths as software matures and gets re-released. And then having an open architecture as well. So the less bespoke you make a solution, the easier it is for it to actually share information between systems and between companies. And the lack of industry standards, there is a much more awareness of industry standards now. We ourselves present our solution in terms of industry solutions and industry processes. So we come with what we see as being typical of an industry approach for how this system is set up and used. And there's a much more open architecture in terms of the plugins that are enabled so that information can flow between systems. So the overall, as looking forward, from a next steps point of view, much more focus around business value and how quickly you can release that value to the business. And the end user experience is now becoming absolutely key, because in the past that wasn't always the key focus. There was a lot of issues around technology and process that were being dealt with, probably at the expense of the end user experience. Moving forward, we now need to start thinking about how we need to be moving away from what we see as a document-centric approach and starting to think more of a systems thinking approach in terms of systems engineering and how we look at problems and the data that sits behind that. And the user navigation of a digital connected data set across the whole ecosystem is a primary focus for us now. We've got a lot of new generation people joining the workforce. I'm going to talk about that on the next couple of slides and the things that we need to think about in terms of that new workforce of the future. So in terms of focus on people then, the next generation, when you look at how these generations have been categorized in terms of workforce, there's a lot of talk about Generation Z. These are the people who were effectively born after 1996. So they're on an age group up till 24. And these people have never really experienced a time before mobile phones. And they basically interact with data on handheld devices all of the time. And they take their information from these devices also. But just to point out that this generation, they basically get their information differently. So they get their digital information predominantly from YouTube. If they want to know how to do something, they tend to go and see how it actually gets done for real, and watch a lot of video content. They can navigate and find information very, very quickly. They don't get their information from traditional sources such as newspaper and magazine subscriptions. And then, like I said, they can explore and navigate and find data extremely quickly. But the key thing to mention here is that they really need to be able to trust the data that they find and act on the data that they find and act with confidence. So it's about presenting them with a trusted data source. So what we're looking at doing is providing what we call a connected data set. We've evolved as a company ourselves, supporting the different industry areas on their journey to become more of a digital twin. We call it the virtual twin, and Paul's going to be following me later. He'll express a little bit more what sits behind the virtual twin. But for the nuclear industry, what we really need to be looking for is providing a structured connected data set that has been validated and approved for use and can be actually used as a trusted source for the next generation that joins the nuclear sector. That's my last slide. Thank you.
Mel, thank you very much indeed. Our next speaker is Richard Jones, who's Head of Nuclear Research and Development for EDF UK.
So my name's Richard Jones. Yes, I'm the head of R&D research and development here in the UK for nuclear. So very briefly, my role is to make sure we're doing the right research and development to support new build projects such as HPC Sizewell C, the current fleet of AGR reactors, of which there are several. Some of those are approaching end of life or are currently being defueled and will enter into decommissioning. R&D supports all aspects of that. And then beyond that, we're into new forms of nuclear, so that could be advanced modular reactors, other forms of fission, even fusion beyond on that. A huge part of what, I'm not a digital person, a huge part of what we do will be around the sciences in terms of chemistry, corrosion, materials, structural integrity, modeling. But of course, there's a big digital aspect to that. We have a head of digital innovation who I work with closely. So yeah, this will be a chance for me just to share some of our approach. I don't think we're fully there yet in terms of recognizing all the advantages of digitalization. So broadly speaking, we've got these 4 programs that support our nuclear fleet in the UK, research programs. We use the analogy of aircraft because that makes it very easy to talk to our stakeholders in terms of where we are with these different technologies. And so we've got our AGR fleet up on the left hand side. These are gas cooled reactors which are approaching end of life, as I've said, so we describe that as a plane safely landing. RWR, we'd be thinking there mainly around HPC Sizewell C, which is a program which has been grown and established. We've got a decommissioning program which is in flight, a much smaller program, may grow in the future. And then beyond that, we're into these much newer technologies and beyond. And all I've tried to do is just to pull out where we see digital as an important part of the future and just tell a bit of a story around that. So our AGR fleet is currently operating and has been for many, many years. There are people that have joined the company and grown up with these reactors. And I think there is a significant amount we could do in terms of digitalization. The challenge for people like me who are pushing on this is that going back to the gentleman's slide just now about different demographics and ages. So new starters and people coming through are expecting to see things to be much more digitalized, where perhaps some of our older demographic that have grown up with these reactors are still very much using older systems, which are inefficient, are slow to use. And that's where we see a big advantage for digitalization. For example, predictive maintenance, using digital tools to predict when equipment needs repairs, reducing downtime. But we also have to do that in the context of we're nuclear, we're regulated, and so that is sometimes seen as a challenge or difficulty, or in some way unsafe to move to some of these new, more modern platforms. So an example there in terms of AGR, we have a huge amount of data associated with the aging of our boilers, associated with our graphite core. It's not considered big data, which was a term that was being thrown around several years ago. I haven't heard it for a while. But when we had someone come in, a consultant, and look at our data, they said, well, actually, you've got a lot of data, but it's at a level that is that level of data, that amount of data is processed by a self-driving car every minute or something like this. And it really put in perspective for us, I think, that although we say to ourselves it is a massive amount of data for a human to comprehend and manage, that isn't necessarily the case for computers and digital. So one of the things we've been applying this to is if you take something like rotational vibration data for rotating plant, there will be huge amounts of data that a scientist or an engineer will have to take from the system. They would have to manually plot that out in something like perhaps an Excel spreadsheet. They would then have to draw their own graphs from that, and then they would go in and do the interpretation, and then they would make a call on what we should do in terms of the right thing for our power station to operate safely. Now, that last bit is where we want scientists and engineers to be using their time. That first part, that manipulation and generation of that data, is the time-consuming part. So we have initiated projects using digital analytics and AI that have allowed us to go in and interrogate that data much more quickly, much more efficiently. And it's how far can we take that is what we're exploring from an R&D point of view. So do you ask it to plot the data and the scientist interprets that? Do you ask it to plot all the data and use some intelligence to focus the scientist's attention on particular areas of data? Or do you go for a full-on chatbot type experience where you ask the chatbot, tell me, based on looking at the data, what we should be doing to operate our plant safely? Now, you really are into the world there of potentially moving away the human experience, the human intuition that a computer wouldn't have, and that's something we need to work with and look at and resolve. But some of the other areas there, graphite workbench, that is something that's fairly straightforward in some ways, but I would still call it digital. So this is where we have new starters coming into the organization, and they're much more used to a phone with an application you click on. And the graphite workbench, what it's done, it's taken all the various models and tools that are developed over many years for our graphite core in terms of how we model its aging. And that could be in a Fortran code, or it could be in a Unix code, or a spreadsheet somewhere, or a report. And rather than having to have a scientist with the knowledge of where all that's kept and how that gets put together, the graphite workbench is a front end that joins all of that together in a very smart and snazzy and quick to use way. And so, and equally on that bottom point there, digital platform is taking the many structural integrity codes that have been developed over many years, which again don't exist in a readily available, easy to use way. That a digital platform will pull all that together much easier for people to be able to use. So I think the story I'm telling with AGR is this is not going to be a revolution for us. We haven't got time to do that revolution given the age of these reactors, but we are evolving where we can and taking a targeted approach where things are hurting us the most, and how we can improve efficiency, how we can make this much easier to use for new starters, and hopefully drive some more value out of those reactors before they come to end of life. It's a different story for RWR. This is where we can take a much more strategic approach. Other countries have water-cooled reactors. So our cousins in EDF Group, which we're part of, they will have many RWR reactors. So we're keen to learn from that side of the business. So there we're looking at full on how can we exploit the synergies in group around digital twins, for example. So how could we have an all singing, all dancing replication of a HPC power plant, for example, when we do an assessment using one of our models. We would update that digital twin. When we do an inspection, we would use the data from that inspection to update the digital twin. And so we are taking a much more strategic approach from HPC. So how can we use predictive maintenance, AI tools to do predictive maintenance, quality assurance. So we already apply, for example, drones on turbine blades as part of the renewables part of the business. We send a drone up, it can take photos of blades, use artificial intelligence, spot where a crack is, make an assessment about that crack, and then report it back to an engineer for decision making. We should be looking to apply those sorts of things to HPC as well in the future. So we're working through that at the moment with HPC and with our IT management team, because there's an important interaction between R&D and us pushing, and IT having to saying to us, well, this needs to fit within the regulation, and obviously our station saying this needs to add value. Another important stakeholder in there will be our regulator. So we're at that level of approach that we all agree that we need to get with the future a little bit more. We can't take the same approach for AGR, and there's a big push there for HPC. I've got one eye on time, and I'll just mention visualization. So we see that for decommissioning, a number of digital innovations. If we can reduce the amount of waste we're sending to underground storage, for example, huge savings there. If we can speed up decommissioning, huge savings there. So we're looking at things like configuration control, which can be done manually at the moment. As your power station enters into defeed and decommissioning, you're changing the configuration of the plant. That needs to be done safely. And we've developed this digital application. There were lots of challenges and barriers there in terms of, I say, changing IT. That's always an uphill battle to do that. Moving to something which is perhaps perceived as less safe initially, and overcoming that barrier. And when it works, it's nice, because then you've got that innovation that shows it works, and it's much easier then to demonstrate that to others around the fleet. And visualization is another one for decommissioning. So how can you show, if I'm going to take this unit out of unit X, let's call it, out of the system during decommissioning, I need to do that safely. I need to do that in a quick and efficient and safe manner. What other other components need to be adjusted and changed or brought off or taken out to allow you to remove that piece, that unit? I liken it to taking a sofa out of a living room. So do I need to move the telly? Do I need to take the window out? And visualization and path optimization to do that travel, to take an item and remove it from a contaminated zone. We can see big value there, and we're making inroads into that as well. Like I've said, I think I've repeated myself to a certain extent with some of this. We are very slow, I think, still to process data and information. It's a kind of 80-20 in terms of 80% of an engineer scientist time can be used collating that data, displaying that data. We want them on the decision making. So there's a big opportunity to improve efficiency. We've started doing some of that. There's more to do at a more strategic level rather than at an opportunistic level. I think we've got to change our culture of innovation. Our role as R&D is to challenge. And the pushback we can get is, for example, the regulator will be seen as a barrier. We don't think that's true. We work closely with our regulator. They've put in place a head of innovation for regulation, and we're working with them on sandboxing and trying to break down some of those myths that nuclear can be digital. We need to do that safely and in the right way, but winning over hearts and minds is a key part of this. New joiners, as the previous presentation said, are digital ready. We find that my children, 10 and 12, they're much more digital savvy than I am. They can find information much more quickly, but we have to be careful. There are things like fake news and trusting in AI all the time, and it removes that human intuition. Where's the line there, and how do we do that in a safe way? AI is coming, whether we like it or not. There's big questions there about the risks and opportunities. Interesting conversation with our regulator about how do you regulate AI. I don't think they know. We don't know. That's a big question. I think how would you regulate something where you have an AI tells you the answer? How would that be done in relation to nuclear safety? And finally, cybersecurity remains paramount. There's still this old technology can be seen as very safe because it's not in the cloud and it's off the grid, if you like. But that slows us down. It's not where we're going and where we need to be. And so we need to work with our IT teams, our operational teams, to overcome that mindset. So I hope that helped. It wasn't as perhaps as a flashy presentation as the previous one, and I don't think we're quite there yet in terms of having it all worked out in terms of digital. Things have moved so fast in digital, and nuclear moves quite slowly. But that's my views of where we're currently at as head of R&D. More to do. We are playing in this area, but there's more to do in terms of understanding the opportunity and how we navigate this journey in an efficient but safe way for nuclear.
Richard, thank you very much indeed. Now it's time for us to hear from John Wolstenholme, who's the Principal Inspector for Nuclear Safety, Office of Nuclear Regulation. John, welcome.
Good afternoon. Thank you very much. My presentation is to give you the ONR's approach to digitalisation. And what I'm going to cover is how we regulate, because this informs how we approach digitalisation and the use of digital technology and application within nuclear as we've seen so far, and our ONR expectations for permissioning a licensee's safety case and sources of relevant good practice that licensees and duty holders can refer to. How we regulate, our philosophy and how this works in practice. We are non-prescriptive and we have a goal-setting approach to our form of regulation. Risks should be reduced so far as is reasonably practical, and this is expressed in terms of reducing risk to as low as reasonably practical before becoming disproportionate in terms of sacrifice, cost, time and money. ONR is focused on enabling regulations. We have good and positive engagements with our licensees. We have open and effective dialogues, and we have common agreed outcomes with those compliance organisations. And we're looking to enable safety cases sort of to be permissioned for licensees' activities. The emphasis in legislation is that the licensee and the duty holders own the risk and they're responsible for the risk, together with the competence of their operators. And they discharge that through having adequate arrangements and safety cases. And we're an open and transparent regulator. We have open and transparent regulatory expectations, and our guidance can be viewed under the resources section sort of on our website. As to how this works in practice, obviously a nuclear site license has a number of license conditions that are attached to it, and the ONR undertakes permissioning activities where we assess safety cases for their adequacy. We undertake compliance inspections, and if necessary, we undertake enforcement, which can range from having conversation with a licensee through emails and letters. If necessary, we have the powers to issue improvement notices, prohibition notices. We have powers under the license conditions, and eventually we're able to take prosecutions and we undertake incident investigations. Next slide, please. How digital technology and how it's applied to the nuclear industry that we've seen so far in the civil engineering area is basically through building information modelling. We've seen it used for structural design all the way from the optioneering stage, from designating safety classifications, from compliance with CDM. We've seen it taken through concept and detailed design for new build and for modifications, and how single and multidisciplinary reviews and third-party reviews are actually incorporated sort of into the design. We've seen it used in constructability, where licensees have been looking at various sequencing and constructability issues, for instance, looking for clash detections of rebar, and they've taken it forward into overall project management and service routing. We've seen it used in asset care and maintenance, where obviously where if you can tag either a structure, a system or a component, this has then generated the maintenance schedules and the maintenance schedule frequencies and the scope of what that maintenance contains. We've only seen limited use in specific areas such as temporary works and demolition, but we have seen the use of virtual reality sets, particularly for space planning of individual plants, interiors, workspaces, the safe accesses that are there, again, clash detection for pipe work and for services and constructability issues. But we are aware of the prospective uses and developments, and there is developing software and application which will benefit both nuclear and conventional safety improvements. And these are linked to the procurement issues of the supply chain, where the supply chain has got access to the 3D model and the data so that they can undertake more effective planning, development and resource allocation. We've seen it used in commissioning, where operating rules have then sort of been defined, because they can run simulations where not only they can train their SWEPT personnel and their operatives and establish the operating rules that are required. We've seen it used in some cases for operational purposes, where monitoring of SSCs has been undertaken for safe and control operation, but primarily also to identify faults and give early warnings of any problems. And we've seen it used in asset care and maintenance, where the focus is on the right equipment at the right time, and it's a fit for purpose scope. And we're hoping that we will be able to see it in the area of safeguards and security provisions and the provision of emergency arrangements. And also for decommissioning and waste, the BIM model is actually an underpinned database of the as-built record, any modifications that have done, plant use, the waste types, sort of, and records. Next slide, please. So our regulatory expectations when we're permissioning a licensee safety case is basically a demonstration of an adequate process and arrangements. And this ranges from the ownership of the design, who owns the design, is it the licensees or on project development group, civil engineers who own the design, or has the design been done by a series of subcontractors in the supply chain who then give it back to the licensee. And we're looking through the chain of command here, through the employer's requirements, the EAR, through the adequacy of the COBE and the data drops that the COBE defines, and the provision of an adequate common database, and what follows from that, the BIM protocols, the execution plan, visibility of the integrated data layers, and the end user applications of how the suppliers actually access that data. And really the data drops, the requirements here are for the key gateway decisions. We're obviously looking for compliance with the law, regulations, and relevant good practice. We have those in our safety assessment principles, our technical assessment guide 17, which I'll refer to later, and through our license conditions, and through various British standards and publicly available documents for health and safety and for security. But essentially, we're looking for assurance, consistency, and reliability of the licensee's intelligent customer capability, the extent of the collaborative working that is undertaken sort of within the BIM model and the BIM package, and the reliability of the original data. And they have adequate systems and software, and there's adequate data exchange between those software packages, and there's no conflicts. And that they have the SQUET people, the trained, experienced, and supervised people to actually input this data and apply this data. We're also looking for adequate handover arrangements from the common database, from the project into the asset information model as the design and the construction develops. And we're looking for adequate peer review arrangements where there is visible, robust challenge and appropriate peer review arrangements, adequate change control of modifications and any alterations, and also capabilities to address any unforeseen or arising design or construction changes. Guidance is available sort of on our website, and I've split this into two. Guidance on our regulatory approach is available on our website at that website address, which will give you more information on our risk-informed decision making and also enabling regulation sort of in practice. But also the website contains copies of the ONR strategy and also the Chief Nuclear Inspector's report. Specifically for assessment and for civil engineering assessment of BIM, on our website, again, at those website pages, you will find our safety assessment principles, a list of all our technical assessment guides and technical inspection guides, and also our security assessment principles. And we have specific guidance in tag 17 of the civil engineering, where there is an appendix annex 2, which details our guidance on building information modeling and what we look for in a licensee safety case. Thank you for listening.
John, thank you very much indeed for coming in bang on time. Our last speaker is Paul Williamson, who is a business consultant at Dassault Systems. Paul.
Thank you, Michael. Right, let's see if I've got control. Excellent. Right, so I'm going to pick up where Mel Temple left off right at the start of today's webinar, and hopefully pick up on a load of the points that Richard and John have made in the last two sessions. So Mel made the point that we need that connected, trusted data set. I'm going to look at what that actually, why we need that, and then how we deliver it, and if time allows, we'll have a look at what it can actually look like. So why we need it. It was a point that Richard made really clearly in his closing remarks about that 80-20 split between the amount of time people spend looking for information and the amount of time they spend actually making decisions. It's about this kind of making the right decisions at the right time. So if we look at the decisions that are made through a sort of a product or a plant life cycle, we start big decisions at the start with a small team in that concept design. We move very quickly into detailed design where we're making lots more decisions. The team's grown, they no longer fit in a single meeting room. You start to lose connection to those earlier decisions. We get into construction, lots and lots of big teams then, lots and lots of decisions, all being made at the same time. Very little kind of personal connection back through to the earlier stages. And then into operations, maintenance, decommissioning, where we've got a completely different team, different generations when we start to look at nuclear, and we need quick, effective decisions. We need the right decisions quickly. So this decision that we need to make down here in the red box, how do we find the bits that we need to know about that have all gone before it? So simple answer is we start small where we can. So in this case, we store things as individual objects. We're looking at a requirement object here. So this is picking out the information around a single individual requirement on our plant. That requirement has got a version and a revision. So we can see, we can look backwards in time to see what it looked like previously, and we can check that backwards and forwards in time. It's also got a life cycle and a life cycle state. So is it in draft? Is it in approval? Has it been released for use, or has it been withdrawn? And then we've got a workflow or a process which is determining the transition between those life cycle states. So that tells us what process was followed, who did what when, and it links us back to that original decision back here. So that's how we're storing things. It's those individual object level pieces of data that we want to pull in and organize. How do we link it back or link it forwards to that decision in the future? So Dassault Systèmes, we've got the RFLP data model that lies beneath a lot of the solutions. So this is how we organize that data. It's not our invention, it's something that NASA came up with, and it's an underpinning principle really of good systems engineering. So that recognizes that your data objects will fit into one of four different categories. Got requirements, fairly self-explanatory, functions or functional breakdowns. So this is the behavior that we want our product or our plant to have. A logical breakdown, also known as a systems breakdown. So this is our systems, subsystems, equipment. What are the physical things that we need to start to have on our site to deliver our product purpose, deliver those functions? And this is where we'd start to see things like 2D piping and instrumentation diagrams, circuit diagrams, sort of showing how things start to relate to each other. And then physical objects, so CAD models, simulations. These are the things that tend to come a little bit later, and we'll explore that in a little bit more detail on the next slide. So all of this is good engineering practice. The key thing about model-based systems engineering and starting to use a platform to link these things up, it's the connections that we get between all of these different data objects. So John made the point about SQEP people. So the data is only as good as the people that are, and the processes that are putting it into these kind of tools and these databases. Good engineering process, good governance is already using these principles most of the time. And at each point of this, when we're looking at that requirement, we're making that change, we're looking at what that's going to impact. That's part of a good SQEP engineering. Nuclear industry is incredibly good at that. What we need to do is make sure we're capturing those connections. So when we're uncovering those as part of that checking process, with the engineers that are already SQEP to do that, we just need to record it. And the output of that is that when we've got this problem in operations, we can have a look at the physical asset that that's related to, and we can trace that all the way back to the requirements, all the way back through the process, and we can find the information that we've got or that we need to find back in the past in that detailed design. Documents, I know sort of documents haven't disappeared, but they, in a system like this, they start to be an output. So they're a way of viewing the information that's held there. So in this case, We want a requirements document, we can generate that from that requirements database. That gives us a snapshot in time of what that looks like. We can see, if we look backwards to when that document was issued, we can see what requirements have changed since then, and why they've changed and who changed them. And similarly, we can output a similar level of sort of requirements specifications, but we can do it from a logical view of a system. So we can start to view that data and output it in lots of different ways. So key things that we see here, so key learnings that we've got from our engagements. If we can capture the connections early, brilliant, because we can capture them in much more fidelity. We can capture them within the engineering processes that are actually checking the information anyway. So you know, these things should come for free if they're part of that process. Where we can't capture it early, so when we look at things like decommissioning, especially at the moment, there's things that we can do further down this trail, but it just means that we start to capture things in slightly bigger chunks earlier on in the life of the plant. That's fine. It still improves that traceability. It still improves the speed at which we can find the information to make the decisions. Different approaches are necessary at different points along this. Second point is think long term. So as I said, this RFLP model is the underlying principle of good systems engineering and good design, really. And it's being adopted across all industries now. What we do see, though, is that the functional and the logical structures start to get put together in a specific systems engineering tool. Our requirements are managed in a separate database. And then when we go into physical design, into detailed design, that all happens in another different system. So the things are being done, but those connections are starting to get a little bit fuzzy. And that's when things start to break down. So think longer term, think about how you're going to use this information throughout that life cycle, and then get that strategy and the right tools in place, collecting those connections as soon as possible. And the third point, really, the kind of AMR, SMR, it's the projects that are right at this early stage. When the project starts, engineers think in 3D. So we can think that all we're going to do is specify requirements, define our functional breakdown, but actually within a couple of weeks, someone's drawn something somewhere. There's a model, there's a picture that helps them to contextualize the information, helps them to understand what's going on. So be ready to capture that, because as soon as that's starting to get generated, it can be useful to everybody else as well. So that physical, don't underestimate how early that needs to be captured. Jumping on to that physical in a bit more detail. Dassault Systèmes, we talk about the triplet model. So this physical model isn't one, it's at least three, and these are big models anyway. First of all, we start out with that layout model. So this is looking at the space claims. It's where things need to go. It's the next logical step from our logical breakdown. So where we've got our piping and instrumentation diagrams, this is when we relate them to geographical space. We then need to make those procurement decisions. So which pieces of equipment are we going to purchase? Are we going to get bespoke made to fit into that layout? This is where our engineering items come in. And then when those things turn up on site and we start to install them, we've got a serialized item. We break these out because we need to know what we need, so and where it needs to go, what we've ordered, and then what we've got installed. And that's partly because we've got different information that needs to be collected against different objects in that. So our non-conformance requests, our certificates of conformance, our quality records are related to a serialized item. Starting to hold those against the layout design gets quite complicated and quite messy. Similarly, operation and maintenance manuals, technical specifications for bought-in equipment, we need to hold those once against the catalogue item, and we need to see where those are used across our design and our engineering items. Second reason that we want to start separating these things out is for reallocation. If we have a problem in construction on a serialized item, on a particular pump that's been delivered, we want to be able to take another one off the shelf that's identical and drop that in its place. That means we need to be able to break and remake these connections under change control, rather than having to start to fix that pump before we can install it. If we tie a lot of these records back to where it's going, we start to really restrict our flexibility and our ability to respond to changes, either in the supply chain or on the construction site. The last point on this, John was talking about BIM. We see BIM as one of the key components of this. This is where we're engaging with the supply chain. We've got different parties, different programs responsible for different scope. We need to bring all that together. So BIM and the CDE is a key part of this, but it's not a single one. A lot of the time on the big projects, we see multiple CDEs because we've got multiple parties at that sort of tier 1 level. But we've also got some information here where a BIM model just isn't the right place to keep it. In the same way that we can't expect our aerospace kind of defense suppliers to use a BIM tool primarily built for construction, we can't expect our construction industry to start using our aerospace grade PLM tools. So we need to have that ability to let all of the different parties use the right tools and the right processes. So
Paul, 2 minutes left, Paul, thanks.
So key points from this: separate out what it is from where it's going, and then secondly, make sure we're looking at process integration rather than tool standardization. So last slide, we can have a look very quickly, 2 minutes, having a look at what this can actually look like in practice. So here we're looking at the front end, in this case, over that RFLP data model. And we're searching for a particular type of pumps. This is a model of pump that we know has been put in the plant. We've searched for it in our product structure. Our product structure has identified 2 different instances of that pump. So we've got 2 of them on the plant. And because we've all linked everything together in that RFLP data model, we can flick between those in that CAD view. So we can see where they are. We can see that they're next to each other. We can also access some of the attribute information against that pump. So we can have a look at the specification and some of the data that's come out of the supplier's information sheets. We get a good idea about what it is, what it's doing, where it fits within its range of operation against the requirements we've got. And then we can also start to explore that data model a little bit more. So this is then starting to explore. We started with the data sheet. We found the model of pump. We found the component parts. We found the locations on the plant where it's installed. We found the requirements and the functional specification for that pump. So all of that is that kind of top view of the that sort of view on that RFLP data model. So that's how we arrange things. The tools that go on top, the VR, the path optimization that the previous speakers have spoken about, all of that is then able to sit on top of that and start to exploit those connections. So that's what I've got, and I'll leave it there.
Thank you very much indeed, Paul. Can I ask a question of my own of the panel? The opening speaker emphasized the necessity for the integrity of the data, knowing where it comes from, knowing it's valid, and so on. Other speakers referred to the Generation Z using mobile devices, AI, ChatGPT, that sort of thing. That is, these systems may find the data is being somehow brought into, is being used with neural networks. Now, if neural networks, at the very heart of them, no one really understands what that particular neural network is doing or arrives at its answer, how can you rely on the safety of the system without knowing how it works? Sorry, Jimmy Green question, but I thought I'd throw it open.
I can start with a sort of a response.
Please.
I'd say that I think using AI to start to make the decisions and enact the decisions I think there's a minefield there that we're not going to get through in a couple of minutes. I think the easier and the shortest or the best way to start using that, though, is to start getting the suggestions. It's start getting the sort of being directed to the information that you think needs to be uncovered quickly. So things like impact assessment. I've got this thing that's happened. How deep do we think this problem might go? I think there's some really simple use cases there where we're using it to speed up the access to information, but we're not replacing the current arrangements and the swept processes to actually qualify the decisions that come out of it.
Yeah, I'd completely echo that. It depends what that data is being applied for. So if you take a really trivial example like writing an article for a team brief on a workshop that we held, which I did recently, I tested an AI to help me write that newsletter, which I then read. It sped up writing that newsletter, and that's not touching nuclear safety. Equally, if it was touching on nuclear safety, you'd want to know the provenance of that data quite exactly. But you can use, as long as you've got that barrier between, I would look at it like that, I guess. You can play in R&D space and use a model that says you've got this type of corrosion going on, as long as there's then that's just directing you to go look there, and you're using everything that you would normally use, that it's safe, and you know where that data comes from, that information, then where's the harm there then? But yeah, it's a big question. But at the moment, that's how we're treating it. It depends what that data is being used for. We're miles away from testing an AI and saying it's telling us to operate the reactor like that, like this. No, that's not where we are. It's a really big question. We can't answer it here, but that would be my.
Okay, thank you very much. Any one of the other two speakers want to join in?
I think it comes down to the licensee having robust peer review arrangements where designs and concepts and developments can go through single and multidiscipline design reviews, and there's appropriate arrangements there for robust challenge. And that really comes down to the SQEP people who are looking at it, knowing what looks right, what the data should say, but also more importantly, knowing where there are faults and shortfalls and the consequences of those faults and shortfalls in inaccurate data.
Okay.
If it's ending, I will just say thank you everyone for joining in. Dassault, Ludovic Drouin from the French Embassy, and Anne Bioche